Okay, so in this movie clip, I'm going to teach you how to get a PN junction diode equation uh, in another approach. Typically, we have take advantage of using the slopes of excess minority carriers in each quasi-neutral region in PN junction diode. That's very conventional and typical approach to get to the ideal diode equation. However, in this movie clip, I'm going to tell you there is another approach using charge control model. So this content is very corresponding to the chapter 6.3. So please take your own time to read and understand fully all the sentences in chapter 6.3. So let's move forward. The very first concept that we have to build up is a minor carrier charge storage. So under forward bias, right? So PN junction diode under forward bias can contain its own certain amount of excess minority carriers in each quasi-neutral regions. For example, the holes can be diffused into the n-side quasi-neutral region under forward bias. And on the other hand, the electrons coming from the n side into the p side can be diffused and stored in the p side quasi-neutral regions. Why is that? Because we are applying a DC voltage across the PN junction diode. In other words, steady state is steady state is valid across the PN junction diode. And then we can come up with this idea. Under forward bias, under DC bias applied across the PN junction diode, excess minority carriers are well kept, well stored in the quasi-neutral regions of a PN junction. So can we build up an equation for excess electron carriers in P side and as well as excess hole concentrations in N side quasi-neutral regions? Can you do that? Yes, it's a very simple question. So let me write down the equation for each. So on the right hand side, I'm going to draw the excess hole concentration in the N side. Okay, so this is N side along as a function of X. Well, definitely this is corresponding to X of N, which indicates the edge of the depletion layer in p-n junction diode. So we have adopted a new coordinate system x prime, and that is corresponding to 0. Okay. Under forward bias, many holes are injected into the n side, and they are going to be piled up. And if I draw the excess hole concentration in n side, that should be follow the exponential function. Okay, like that. So this indicates delta p sub n as a function of x. Okay. Previously, when we are deriving the ideal diode equation, we have taken advantage of using the slope of this curve. Okay, in other words, we have used round delta p sub n x prime round x prime. So please go back to the old derivation steps for ideal diode equation. Then you're gonna see this first derivative of excess minority carrier concentration. However, herein we're going to use the minority carrier charge storage. So how much excess carriers are well kept in the n-side quasi-neutral region. So for that purpose, we should estimate the area of this curve. So the physical meaning of this area is total charge, total number of holes kept or stored in the n-side quasi-neutral region. So how to estimate it? So as described here, the total amount of charge of holes in the n-side is this. Once we sum up all the excess hole concentrations along x direction and y direction and z direction, okay, and think about the unit, that is, the number of holes per cubic square centimeter. And since I'm doing integration for x, y, and z, so these the unit for volume would be cancelled out. So herein the total number of holes are left, but on the left hand side we need a total charge. So one more time, coulomb per unit. Okay, so unit charge times concentration times volume will give us total charge. So here unit charge Q times, what is this A? Yes, along Y and Z direction, all the excess hole concentrations are uniform. So if I cancel out two integrations and cancel out dy dz, that it would turn out to be cross-sectional area of A of p-n junction diode. So go back to the p-n junction diode again. Previously we have done all the analysis along x direction. Y and z direction we didn't care too much because all the physics that happened along x direction is identical along y and z direction. Okay, so this cross-sectional area has been denoted as A, and two integrations along y and z are estimated, and it turned out to be A, which is cross-sectional area of p-n junction diode. Okay, what about the x? All the excess hole concentrations are existing along, from x of xn to infinity. So since we should estimate the total hole concentration, we should estimate the area underneath the delta p sub n of x plot. So from x of n to infinity, we should sum up all the excess hole concentration in n side. Okay, so this. So total charge, total holes stored in the n side quasi-neutral regions can be written with this equation. The next job is how to do the integration calculation. This. Previously, I guess we have learned using diffusion lengths of hole, we can simply estimate the total area. The concept is this. Once we know the here delta p sub n at x of xn, or delta p sub n x prime is 0. Once we, with the initial value of excess hole concentration, and let's say this distance is corresponding to the hole diffusion length. So let me change the color. And this total area, blue colored area, is identical to the hole concentration, the total charge coming from the holes stored in the n-side quasi-neutral region. So this alternative derivation for minority carrier or hole charge stored in the n-side quasi-neutral region has been well explained in the previous movie clip. So go back to there. Okay. All right. So the initial value of excess hole concentration times diffusion length. So this blue colored area is identical to the red colored area. Okay. Well, if you intuitively, you may have yourself understood that the LP, L sub P, hole diffusion length is indicates the concept of average distance, how long the excess hole can diffuse in the inside material. Okay, so that the initial excess hole concentration times average distance uh, along which the excess holes can travel into the antimaterial would be almost identical to the whole area or whole, the value obtained from the integration of this. Okay, so we have done uh, to write down the equation for Q sub P, which indicates how much holes are stored in the inside quasi-neutral region under forward bias. So similarly, because this is p-n junction diode, so similarly, the electrons coming from the n side into the p side, injected into the p side, would also be derived, and everything would be very same as the things that we have learned for the n-side quasi-neutral region. So let's repeat it, but other than this sign of electrons charge minus q instead of plus q here, because we have talked about the hole on the right hand side, but now we should talk about the electrons. So take care, there is minus sign. All right, so let's write down or draw the how the excess electrons are accumulated or stored in the p side. So delta n sub p x. So definitely this direction indicates x, but we are going to adopt x2 prime new coordinate x system. So x2 prime is 0 here. That is corresponding to the x of minus xp. So this indicates the depletion layer's edge on the p side. So many electrons would be injected into the p side, and they're gonna be piled up and stored like that. Okay, so we have derived the full equation for delta n sub p as a function of x, or x2 prime. So this indicates a p side. And just to refresh your memory, what was the equation for delta n sub p? That was np naught times exponential qva over kt minus 1. Okay, so please go back to the whole processes for ideal diode equation. Then you're gonna get to the how to get this delta n sub p of x prime, x2 prime. All right. And similarly, as we have done for whole charge storage on the n side, let's repeat how much electrons can be stored in the p side. So I'm talking about this area. So this area has been denoted as q sub n, as also shown in here, q sub n. And this q sub n should be integration of all the electrons coming from n side into the p side, x, y, z direction. But since y and z directions are identical, all the physical events are happened along x direction is identical and valid along y and z direction. So these two integration and dy dz will be combined together as A, which is the cross-sectional area of PN junction diode. And here along the x direction means from minus xp right here to what? Yeah, minus infinity. So minus xp to minus infinity, we should sum up all the excess electron concentration in the quasi p-side quasi-neutral region. So as we have done, let's switch the color. So instead of doing calculation to obtain the total area underneath the plot of delta NP x2 prime, let's do this. For a given initial value of excess electron concentration, they're gonna be traveling to the p side on average by Ln. Okay, so this blue colored area should be identical to the red colored area. So this estimation for area makes our life much easier because this blue colored area can be simply obtained by multiplying the side length and height. Okay, so the side length is L sub n, the average diffusion length of excess of electrons in p side, and this delta np at x of minus xp here is the initial value of electrons injected into the p side. Okay, so the total charge stored in the p side, I mean the stored charge of electrons injected into the p side, uh, can be written with this equation: minus q times a times delta p and p of minus xp times electrons diffusion length in the p side, definitely. Okay, so in this slide we have summarized and derived qn and qp as a minority carrier charge storage. So for a given PN junction diode, now the forward bias has been applied, so that is depletion layer. So many holes are injected into the N side and many electrons are injected into the P side. So now I'm talking about how many holes are stored in the N side because DC bias has been applied across PN diode. So certain amount of holes are kept, well stored in the inside quasi-neutral region. So the question is how much total charge can be stored in the inside by hole. Sorry about that, P in the inside. Okay, so that was Q times A times the initial value of excess hole concentration in the inside at the edge of the depletion layer times L sub n, no, the L sub p, the whole diffusion length in the n side, right? Okay, so QA initial value diffusion length that indicates the minority carrier. In this case, because we're talking about the n side, the whole minority carrier can be stored in the n side, and the total amount of whole concentrations, whole charge, the total amount of whole charge in the n-side quasi-neutral region can be estimated using initial value times diffusion length and cross-sectional area and unit charge. So please remember these are simple equation to estimate how much magnetic carriers can be stored in the quasi-neutral regions. So similarly, we can repeat and estimate how much electrons can be stored in the p-side quasi-neutral region. So now we're talking about the electrons, so minus q, electrons unit charge times cross-sectional area times initial value of delta n sub p at x of xn times electron diffusion length L sub n. Okay, so think about this situation under forward bias. Now we have successfully derived the equation for red colored area. Okay, so now we have completed ourselves with good gears to derive ideal diode equation. So to get to the ideal diode equation, let's start. Let's begin with this slide. Let's consider forward bias the PN junction again. Okay. Okay, let's consider a forward bias PN junction and the total excess hole charge in the inside the quasi-neutral region is QP. That was derived in the previous slide, right? Q times cross-sectional area times, this whole integration is equivalent to the delta P sub n x of n times LP. Okay, and in the second step, let's get the minority carrier diffusion equation again herein. So for a given PN junction diode under forward bias, the holes can be injected into the N side, right? And those holes, okay, PN forward bias, holes are injected and they're going to diffuse throughout the N side. So these physical events can be explained with the minority carrier diffusion equation. That was actually originally second order derivative equation. So without the generation by light, we can write down the second order partial derivative equation for minority carrier diffusion. So please go back to the minority carrier diffusion equation if you would like to review and refresh your own memory. Okay, please do that. All right. Number three, uh, since we are looking at how holes are diffused in the inside the quasi-neutral region. So in this quasi-neutral region, the electric field is very small, right? I mean, the externally applied voltage should be about 100%, almost 100% of externally applied voltage VA is well delivered and well dropped across depletion layer or junction. So junction voltage is almost identical to the externally applied voltage V sub A. Why is that? Because depletion layer indicates this region is depleted of electrons and holes, meaning that there is uh, no carriers to flow current, so that in terms of resistivity or resistance, you know compare against the resistance value coming from P side and N side quasi-neutral region, the resistance for the depletion layer is super high. So three different series connected this and that, right? So this resistance value is super high, higher than the other two resistance value for quasi-neutral regions, so that the externally applied voltage is well 100% delivered to the junction area. So that is the reason why there is no voltage drop across the quasi-neutral region, so that we can simply estimate that the electric field in the quasi-neutral region is very small or almost zero. So that's the reason why we are only talking about the diffusion mechanism instead of drift mechanism when we are talking about the current flow in quasi-neutral region. All right, so the hole are now injected into the inside and they're gonna be moved by diffusion mechanism. So the current density of holes would be determined by JP diffusion plus JP drift. However, this drift component can be very negligible because electric field is very small, so the diffusion current component has been left behind. So previously we have learned how to write down the equation for diffusion current. If you have missed how to how to describe the diffusion current density of hole, please go back to the previous previous slides for that, and please refresh your memory again. Previously, we have learned that the hole concentration uh, diffusion current can be uh, how much the concentration gradient are necessary to form the diffusion current. So here the delta p sub n. So I'm talking about here in the n side sub n. So this slope, the value of first derivative of delta p sub n is corresponding to the concentration gradient. So this concentration gradient times diffusion constant times charge indicates hole current density. Okay, and let me name the equation with this is equation number 1, this is equation number 2. Uh, let me see. Okay, so here from equation number 2, dp times round delta pn round x is identical to the minus 1 over q times jp. Okay, and let's take derivative with respect to x one more. So x round x. Okay, and let's plug in this equation into equation number 1. So herein you can see the dp second derivative of delta p sub n. So herein, okay, so for this term you can plug in this value into here. Okay, then you're gonna get this equation round delta pn round t is equal to minus 1 over q jp. One more derivative, right? Because we have additionally taken the derivative with respect to x, and here minus delta pn divided by tau sub p. And let's multiply plus q for both edge. So here plus q, and it's going to be cancelled out, and there is one more q. Okay, as this q is constant, you can have q get in this term q. Okay, so you can see this equation, and the minus jp over round x, you can see that, and here minus q delta pn over tau p, you can see that. Okay, let's name it as number 3, equation number 3. Okay, so remember the equation number 3 and bring it here. So equation number 3, let's do one more integration, but along quasi-neutral regions. Okay, so now let's do integration over the n-side quasi-neutral regions. Okay, then you can see that here this integration and y and z direction. Okay, and here y and z direction integration and x direction integration. But previously the equation was minus round jp round x. So then this round x dz are cancelled out, and y and z to integration would become A. So A times minus from JP. Definitely all the quasi-neutral region along, all the piece inside quasi-neutral region along x direction. So minus A can be found here, and all the quasi-neutral region means from xn to plus infinity along dj sub p. Okay, and the third term, the second term on the right hand side was q delta pn divided with tau sub p. So if I do integration along x, y, z, so yz would become a, and minus q left, and the tau p is kind of constant, and integration delta p sub n along x from xn to infinity. Okay, so here in minus, okay, q is here, 1 over tau p is here, and a is here, and delta p sub n, uh, from xn to infinity. Okay, so we got all the terms. Okay, so this result comes from the integration work for equation number 3 shown in previous slide. All right, and now let's take a look at, let me erase all the inks that I have drawn. Uh, if you need your own break time, please stop my movie clip and take your own break time. That would be very the best way for you to keep concentrating my movie clip and my materials. Okay, so take your own rest time whenever you want or whenever you're convenient. Please do that. That is a good way for listening to the pre-recorded movie clips. Okay, so furthermore, in a P plus N junction, so previously we talked about the PN junction, but now let's narrow down our focus onto the P plus N junction. Then the equation above can be more simplified like that. So let's do that. Before moving forward, what was this, by the way? Qa times x into infinity delta p sub n dx. What was this? Yes, Qp. That has been introduced in the very first slide. Let's go back here. Qp was Qa. This. Please remember it. Okay, let's move forward. Yes, herein, right? So this whole this term can be replaced with a total charge stored in the inside by holes. Okay, so same term can be found on the right hand side, that is identical to the QP. Okay, so now QP has been, once you take a derivative of QP with respect to time, okay, that term can be found. That term can be found here. Okay, under fold bias, the charge stored in the inside by holes as a function of t, time, okay, is equal to what? Yeah, the answer can be found from this equation. By the way, the second term can be simplified as minus qp divided by tau p, so you can get this. Okay, what was this, by the way? Under fold bias, the holes are injected into the inside. and that those holes are stored and kept in the inside quasi-neutral region. That total charge has been divided by tau sub p, which is the minority carrier lifetime. So the unit of QP is Coulomb. Tau p, the unit of tau p is second. So Coulomb per second, which is amp, the unit for current. So how the stored charge can be varied as a function of time will be determined by two factors, number one and number two. So this number two factor indicates kind of recombination rate, right? So that you may come up with the continuity equation in your mind. Continuity equation said how much current is flowing while the current is flowing, part of carriers would be recombined with majority carriers in inside region. That was the continuity equation. If you would like to refresh your memory again, please go back to the slide for continuity equation. Then you will see that a simple infinitesimal volume and the current is flowing, input current and output current at x plus dx, and some magic can be happened within this infinitesimal volume. So the magic was a recombination and generation. Okay, so in terms of equation format, quite similar to the continuity equation. Okay, so the very first term on the right hand side would be the current flow. Okay, so let's do this. The first term on the right hand side has been rewritten here again. And let's do integration. Here 1 is there, so minus a times jp from jp xn jp infinity, then minus a jp infinity minus jp xn, then minus a's are multiplied to each term, then you're gonna get this equation. Okay, by the way, this jp at x of infinity is almost zero. In other words, in p-n junction diode, once hole is injected inside, and if it traveled toward and arrived at x of infinity, how many holes are alive without any recombination with electrons in inside material? Nothing. Therefore, the current component coming from the holes at x of infinity must be zero. Okay, nothing left at x of infinity. Okay, so you can ignore this term, then you're gonna end up this. Then what about this? Cross-sectional area times the current density by holes at x of xn. So I'm talking about this at the edge of the depletion layer, x of xn, how much current is diffusing. Okay, so kind of initial value, right? So that initial value has been denoted as I diffusion. Okay, so just for your information and to have you better and easily understand what's going on, how the diffusion current is forming, let's do fluid analysis. Fluid analogy. So here is water faucet. Okay, and now the water is supplying into a big tank. So this water droplet is corresponding to holes, and many holes are now stored in the n-side quasi-neutral region. Okay, and for some reason these holes would be recombined with electrons by recombination. So in this fluid analogy, uh, part of water would be leaked out. This loss due to recombination, okay, in terms of QP over tau P. Okay, so this current component holds now diffusing in or at x of xn, right? So this diffusion current can be denoted as I diffuse, or which is corresponding to cross-sectional area A times J sub P whole current density, where at x of xn, the initial injected value of holes. Okay, so under forward bias, definitely a certain amount of holes should be injected into the n side. So that amount can be described as J sub P at x of xn. Okay, so we have successfully derived this equation, but in terms of diode, in terms of equation format, that is very similar to the continuous equation. Certain value are now varied by time, but that how much, how varying, how time varying variable here in Q sub P can be determined with the two terms. How much is supply has been included and how much loss has been considered when the current is flowing, when a certain particle is moving throughout an infinitesimal volume. Okay. Okay. So now it's time to do the build up the charge control model. So we can calculate PN junction current, the diode equation, in two different ways. The very first one is very typical and conventional, and we have spent many hours to derive excess electron concentration and excess hole concentration in each quasi-neutral regions under forward bias. Afterwards, we can develop the diffusion current component, and lastly, we can sum up two current component at x of xn or at x of minus xp, then we can build up the whole shape of PN junction ideal diode equation. What was that, by the way? Yes, the current was saturation current I naught times exponential the applied voltage divided by thermal voltage kT over Q minus 1. Okay, this is the ideal diode equation. So from now on, let's derive the ideal diode equation in another approach. Take a look at the number 2. From steady state. From steady state means under DC bias, right? Qn and Qp, the electron concentration in the p side and hole concentration in the n side quasi-neutral regions. Those excess electrons and excess holes are stored in each excess minority charge distribution. So in the right previous slide, the excess hole concentration, the total charge coming from the excess hole concentration can be written with this equation. But now we are talking about the steady state. So as time varies, the holes stored in the n side would never be modified. I'm talking about this in PN junction diode. now the DC forward bias has been applied. So hole has been injected, and that hole, if I draw the excess hole concentration along x direction, this hole concentration, this plot, can never be the function of time. Once it is shaped and built up, this plot can never be affected by time. As time goes by, this plot, delta p sub n as a function of x, has never been modified. That is a steady state, right? So that this area, QP, can never be changed by time. In other words, if I take the derivative of QP with respect to time, that should be zero. That has been used here. QP divided by dP is identical to 0. By the way, this QP, dQP over dt, was written as what? Yes, there we go. Take a look at this equation again. Okay. Then this is I diffusion. That was A times current density at the edge of depletion layer. Okay. So using this equation under forward bias, A times Jp at x of xn is, let's move it onto the right hand side, then you're gonna get this. And since this is a cross-section area current density, so if I multiply both of them, I'm gonna get the whole current at the edge of the depletion layer xn. Okay, so we're gonna get this. Take a look at and think about the physical meaning of this equation. What was the QP? Yeah, under forward bias, hole has been injected into the N-side, and those holes are well stored in the N-side quasi-neutral region. So how much charge has been stored in the N-side quasi-neutral region? That was denoted as a Q sub P. And what was the tau P, the physical meaning of tau P? Yes, the injected holes into the N-side can survive without any recombination with electrons in the antimaterial, right? So tau p indicates the average time, how long the injected holes can survive without any recombination with electrons. So Qp divided by tau p indicates how much current can be formed by injected holes from p side into the n side under forward bias. Okay, so this I sub p is actually the current value under forward bias. Okay. So similarly, we can repeat this equation for dqn dt is equal to ajn minus xp, the depletion layer edge on the n side, right? Minus xp minus qn over tau n. But since the polarity of electron is opposite to the polarity of holes, so I have used the plus. Then under forward bias, this value, I mean the excess electron concentration in the p side, has never been affected by time, because now we are talking about under forward bias at steady state. So A times Jn minus xp is equal, because this is 0, equal to minus Qn over tau n. And this can be rewritten as In at minus xp. Okay, so In minus xp is equal to minus Qn over tau n. That was described again here. Okay, then now we have successfully derived Ip and In. Then we can estimate the total current across PN diode. So current I is equal to Ip at x of xn plus in minus xp. How come the summation of these two components can become the total current? Why is that? Definitely no recombination generation in the depletion layer. This assumption should be used, otherwise we cannot build up this equation. Okay, now you can plug in simply here and there, then qp over tau p minus qn tau n. All right. Okay, and qp. Let's go back to the first slide. qp, what was qp? Here. This guy. QA, initial access hole concentration times diffusion length. So remember it. Let's take it and plug it into here. Okay. And what about the QN? Let's go back to the first slide. Okay. Here, QN was minus QA, initial value of access electron concentration in the p side and electron diffusion length. So remember it and take it into here. Then you're gonna get this equation, Q A delta NP minus XP ln over tau n plus QA delta P sub n xn LP over tau P. Okay, and oops, I guess I have missed the minus sign here. Okay, then you're gonna think about this value, the initial access electron concentration in inside delta NP minus XP. What was this? Yeah, NP naught times exponential QVA over KT. If you cannot remember what this equation is, please go back to the whole steps for ideal diode equation. Then you're at the very first step, number 1, you can see that excess hole concentration, excess electron concentration at the edge of the depletion layer can be defined as NP naught times exponential VA over KT over Q. So this NP naught indicates abnormal equilibrium in the p side, the electron concentration. So since the p side has been doped with the Na, so Ni square 10 to the 10, right, times QVA over KT. All right. What about the delta Pn? Let me write down here. Delta Pn xn is identical Pn naught times exponential QVA over KT. And this Pn naught indicates abnormal equilibrium in the n side hole concentration. So n side is doped with n sub d, right, times exponential QVA over KT. So this and that should be plugging into this equation, and you're gonna end up with all other variables and terms are combined into a single term as I naught times exponential QVA over KT. Okay, so this equation I is equal to I naught times exponential QVA over KT, which is the comes from the ideal diode equation. So in summary, using this charge control model, instead of doing very complicated analysis to get to the forward bias, the current value of PN junction diode using the slopes of delta NP and delta PN. We can simply use how much excess electrons and holes are stored in each quasi-neutral regions, and under steady state, under DC bias, using this condition, we can simply estimate how much diode current can be flown across PN diode. Okay, so this is a charge control model. The last slide before finishing this movie clip is this charge control model for narrow base. Previously, we have learned the long base PN junction diode first. Afterwards, we have derived a very complicated equation for narrow base PN junction diode. So let's repeat and do the same work with the charge control model. So what if the length of base it becomes very narrow? Then what would be happened? So remembering the excess carrier concentration has been modeled with the exponential term, but for a given narrow base PN diode, the excess carrier concentration plot and distribution can be linearly modeled. That was a key idea, right? Or key difference from long base PN diode. So for a narrow base diode here, you can simply replace tau sub p or tau sub n by what? By minority carrier transit time, tau sub tr transit, tr travel, tr here. So transit time, tau sub tr, we can get the equation for tau sub tr in the end. So before moving forward, how much time is required for minority carriers to travel across the quasi-neutral region? So I'm talking about here. So for a given PN diode, but here in the base width is very limited. So this is xn, this is xc. Instead of infinity, I have used a kind of constant value to indicate the edge of the n-side quasi-neutral region. That means we are talking about the narrow base. Originally, whenever we are talking about the position of the edge of the quasi-neutral region, that was matched to the x of infinity. That means a long base. But now, since the physical width of the n-side is very limited, so that instead of infinity, I'm going to use a certain constant value. Herein, I have used the x sub c. Anyhow, under forward bias, right? Under forward bias, the holes are injected into the n-side and they're going to travel across the n-side region. But the question is how much time is necessary for these minority carriers in n-type material to travel across this narrow base. Okay, so let's calculate that time. Basically, that time would be matched to this minority carrier transit time. So transit time, the concept of transit time is this: for a narrow base, once under forward bias, hole has been injected and hole is now moving toward the edge of the n-side region. How much time is necessary to move completely across this n-side narrow base or n-side quasi-neutral region? How much time is necessary? Well, the answer is minority carrier transit time, tau sub tr. So let's calculate it. On a narrow n-side, hole has been injected. Then how much holes are stored in the n-side quasi-neutral regions? Previously, we have done and developed the equation for that. QA and all, you can sum up all the excess hole concentration. But herein, notice that instead of infinity, I have used the Wn. Wn means here x of xn, the edge is defined as Wn. Okay, so Wn indicates the width of the n-side material. Okay, and one more thing is, if this Wn is much smaller than infinity, then X as a whole concentration as a function of X in the n side. Here Xn, so this is n side, okay? If we are talking about the long base, the curve for delta Pn is following the exponential curve. However, for a narrow base, this curve would become linear, okay? We have learned in the previous movie clip, okay, for a narrow base. And here the edge is Wn, okay? All right. So since QP indicates the area, right? So this line is following, this is a straight line. So to estimate the area underneath, it's very simple. It's a triangular, right? So this whole area is corresponding to 1 over 2 times the side length is Wn minus xn, but that was denoted as Wn prime, that is Wn minus xn, okay? And the height, this height, that value is delta p sub n at x of xn, the initial value, right? So delta p sub n at x of xn. Okay, then now we are talking about the transit time. So once we know the how much whole charges are stored divided by how much current is flowing, then we can simply estimate the transit time. So let's estimate how much current has been formed by the injected holes. So current component, whole current can be defined as cross-section area times current density, and this current density, A, minus Q times dP delta Pn divided by dx, okay? So this, let me see, d delta Pn dx, what was this? Since now we're talking about the narrow base, so delta Pn x, right? And now we should calculate the d delta P dx. That is the slope, right? Is d delta Pn over dx. Okay, so the slope is very simple. The final value of y-axis is 0, right? First value is here. So final value minus first value delta Pn at x of xn. And the final x value is Wn or Wn prime, and here the first value is xn or 0. So I'm talking about if I'm using the x prime coordinate system, this Wn becomes Wn prime, and this xn becomes 0. So 0, no, Wn prime minus 0. Okay, so plug in this value into here, then minus Wn prime. So Wn prime here minus delta Pnxn, and this minus would be cancelled out. So you're gonna get this equation. So now we're almost done to get minority carrier transit time. Tau of Tr is Qp over Ip, because you know Ip is Qp times tau of Tr. So here Qp should be plugged in here instead of Ip. This whole value has been included here. So let me erase my ink. So simply you can divide this term divided by that term. Then Wn prime are cancelled out, Qa are cancelled out. So 1 over 2 delta P sub n, delta P sub n. So they're gonna be cancelled out. dP left, and no, Wn should be move upward. So the transit time of Hall will become this Wm prime square divided by 2 times dp. So this Wm prime dp is kind of constant. Diffusion constant is, using a Einstein relationship, KT over Q, for a given temperature, the diffusion constant, the ratio of diffusion constant to mobility is constant. So mobility would be determined by n sub d in the n-side material. So dp is kind of constant once a doping concentration is given. And Wm prime is, this is a narrow base p-n junction diode, so you may define the physical length of the n-side. So the whole transit time, tau of TRP, is very dependent of diffusion constant or doping concentration and physical width of the n-side material. All right. So you can repeat all the steps for holes injected into the n-side for the electrons injected into the p-side, narrow p-side definitely. Then you're gonna get the similar equation for that. Here WP prime indicates this. Depletion layer, p side, n side. So this along x direction, that depletion edge is minus xp. But since if we are adopting new coordinate system x2 prime, that is 0. And this edge, if this p side is long base, then this x value is minus infinity. But since we are talking about narrow p side, so this h corresponding to x2 prime coordinate system, x2 prime h of p side is equal to wp prime. Okay, so this value is wp prime. So if this is wp along x coordinate system, wp minus xp is equal to wp prime. Okay, all right, so that's all for the charge control model. Okay, and that is corresponding to the chapter 6.3.1. Okay, so please read all the sentences for the chapter 6.3 and try to understand what the charge control model is. And while we are studying the charge control model, we have successfully derived the diode equation as well under fold bias. And also for long base, we can estimate quantitatively how much electrons can be stored in the p side and how much holes can be stored in the n side. So for given forward bias VA as described here, we can quantitatively estimate how much charge can be stored in the n side and p side. Even in narrow base case, if p side is narrow or n side is narrow, or for simply speaking for short base p-n junction diode or narrow base p-n junction diode, we can also estimate the total charge stored in the n side and p side. But the only difference between this long base and short base, is this. Instead of Ln, you can use the real physical width of a p side. Instead of Lp, the whole diffusion length. Always think about when you are talking about the diffusion length in p-n junction diode, that should be for minority carrier. So in which reason the whole can be minority carrier? That is n side, right? So instead of LP, you should WN prime, the narrow base for n side material. Okay, and here in the minority carrier transit time, tau TR has been derived fully. So the narrow base width and the diffusion constant, those stuff would be used to get transit time. Okay, so in the upcoming movie clip, I'm going to explain the small signal model as well as transient response, so which is corresponding to chapter 7 and 8. So by taking by listening my movie clip of this, you should review all the materials in chapter 6 of BRS book. So please review, and see you in the next movie clip. Bye bye.